Okay. Good morning, everyone. Today we continue with epidemiology and public health. And it's going to be mainly about investigation of outbreaks, foodborne illness outbreaks. Okay. We were here last time, incubation period, and we showed that if you look at this list of causative agents, you will see that the incubation period is a range. And this range can be narrow range and wide range. If you look here, the blue is the narrow range, the most common, and the green one is the wide range. Okay. And if you look, you can see that one of the applications of the incubation period is the quarantine, isolation of sick people. You have a contagious disease, infectious disease, and you want to isolate people. This is what we call it quarantine. And where did this word quarantine come from? It came from the Italian word quaranta. Quaranta means 40. 30, 40, 50. 30, 40, 50. Giorno is day. 40 giorni, 40 days. The Italians used to practice this during the plague in the 14th century, when they used to isolate people for 40 days. And when they showed these people who were isolated, when they showed symptoms, then they have the disease. When they don't show symptoms, then they are allowed to enter the country. Okay? So it's 40 giorni, 40 days quarantine. If you look here, we have the estimation of incubation period. As I told you, estimation of incubation period is usually nowadays is in the literature. If you go, let's say, to any disease in the literature, they will tell you what is the range, the minimum, the maximum, and the average in the middle. Okay. We have this, just a moment. Okay. We have here this outbreak by Salmonella. And if you see Salmonella typhimurium, incubation period for 190 persons. Okay. If you see here that the incubation period can be as little as or as short as days, like flu. Flu, you get the infection just within a couple of days. Sometimes you get the infection or the disease or the adverse health effect after 20 to 30 days, 30 years. Example is asbestos. When you are exposed to asbestos after 20, 30, 40 years, it will cause a cancer in the pleura, which is the membrane surrounding the lung. This cancer is called mesothelioma, and it takes years and years, decades, compared to days in common cold. If you look at this, this is the Salmonella typhimurium outbreak, and you look at the yellow curve here. You see the yellow curve here? The yellow curve here. The yellow curve represents classic epidemic curve. Good. The yellow curve here is the classic epidemic curve. Classic epidemic curve, it's the number of cases versus time. So day one, we have this number of cases. Day two, we have this number of cases, and so on. They say that if you plot the number of cases versus not time, but rather the log time, you will get a normal curve like this one here. Normal curve, like this one here. And if you take these numbers and plot them on a log normal graph paper like this one, you will get a linear curve, line. And through this line, it can help us identify the incubation period for that outbreak or that disease. Of course, things are not as easy as this, because if you look at if you go to the literature, PubMed, you can find that several Chinese groups have identified the incubation period for COVID-19 in a very different way. Some of them used Monte Carlo estimation method. Some use this method. Some used integration and purely mathematical methods until all of them reached up to the mean incubation period, the mean incubation period, or the average incubation period for the COVID-19, 5.6 days, almost 6 days, or the range minimum 2 to 14, and a wider range 2 to 27. So things sometimes might not seem as simple as they look in teaching, okay? But you can go to PubMed and just write incubation period or estimation of incubation period for COVID-19. Several papers, okay, and very nice papers. Linear graph because they made the time into log of the time, log 10, and then after this, all the numbers on this here, they made it plot on a log normal graph. You see here, it's not log. It's not a normal graph, it's a log graph. They plot it, and then they get the number, and then they try to match. Of course, as I told you, things are not as easy as they look, but this is one of the methods, not all the methods. There is also what we call estimation of time of exposure. I will explain it in a minute. Okay, outbreak investigation. We have three critical points. One, time of exposure. When did the exposure happen to us? Imagine that we are in a party, yes, and some of us developed diarrhea, vomiting, and these classical symptoms of an food outbreak. Okay, when did it happen, the exposure? It happened during the party between, let's say, 6 o'clock and 8 o'clock in the evening. Time of symptoms. When did the symptoms appear? The first symptom, in the first case, it appeared 3 o'clock in the morning, next day, or 7 o'clock in the morning, next day. Incubation period, how long? We have to either, we go to the literature. Of course, we have to know that this outbreak is caused, let's say, by Salmonella, or Shigella, or stick, Shiga toxin E. coli. Then we go to the literature and see, this is the range, it's 2 to 10, and the average is 4 from the literature, previous records. Okay, so we have these 3 points, and if you know 2, then the third would be calculated at least. I am going to show you here, just a minute. I am going to show you time of exposure. How do we calculate it? Just very quick. Okay, have a look. Of course, this is a new video. I am not going, it has my voice here, but I am going to mute it so that I can explain it very quickly without double voice of me talking 2 times, okay? But you can go to the video and have a look at it. That's just, I posted this 2 days ago, not more. Okay, just make this like that. And then look, exposure time estimation. Look, this is the definition of incubation period, time from exposure of causative agent, bacteria or virus or any, until the first symptom appears or symptoms. And usually, as we said, usually it's the characteristics of each disease agent. Each bacteria, each virus has its own incubation period. Some days, some weeks, some months, and some years. Okay? And a patient appears normal, as we said last time. Patient appears normal. It's only at the end or the second half of the incubation period that you as a patient might become, or definitely you will become infectious. You will look normal, but still you will infect others. Yes, in the second half usually. So this is the problem. Some people were in a party and they had symptoms caused by Shiga toxin producing Escherichia coli. It's a bacteria, enteric bacteria. Stick, we call it stick. And look, December 9, 8 cases. December 10, 12 cases. December 11, 7, 5, and 2. What is the most likely exposure period? When did they get the disease? Just to show you how they calculate this. So usually epidemiology and statistics. Look, from the PubMed literature, we know the range minimum for such outbreaks caused by stick is 2 days minimum. Maximum 10 days. Average around 4. This we know it from the literature. Okay. Based on this, let's calculate the time of exposure, the estimation. Let's plot. Good. So this is 8, this is 12, this is 7, this is 5, and this is 2. So construct a histogram. This is a histogram. And if you look here, if you look, the yellow graph, it's a classic epicurve, epidemic curve, classic. The one which we talked about, 2, 10, and in the middle there is 4, it will appear like this. That's the classical way. Look, of course, if you get a curve like this, you have to know that you are dealing with a single source CVE, single source common vehicle exposure. If the curve is like this, time. People do it versus time, but mathematicians, they like to do it versus log. Anyhow, if it looks like this, then this is single source CVE. Okay. If you remember those we got from literature, 2 days, 10 days, and 4 days average, it should look like this. But all the time, reality is different from theory. Okay. So the first thing is we have to identify the average, identify peak. This is the peak, 12 cases, and it's going to be 10th, December 10th. And now determine the average incubation for this outbreak. How? If you remember, our average was 4. Remember? Our average was 4. So this is the peak. We go back 4 days, which is 6. We go back from this peak 4 days because the average in the literature tells us that the average is 4. So we go back 4 days. So the average is 6, December 6, the average. Okay. That's how it looks. Then we are going to determine the minimum. Now the average determined. Now we go for the minimum. The minimum, we have to select the first case or cases. They are December 9th. They started here. And if you remember, the minimum was 2. Very good. So you go back 2 days. You go back 2 days. So 8, 7. So this is the minimum. So minimum is 7, average is 6. Now maximum. Maximum, we have to go where? To the last. Now we go to the maximum. Maximum there is 10. Here is the last case is 13. We go back 10 days. 10 days means we are going to reach 3. So it's 3, 7, 6. 3, 7, 6. That's how we do it. As I told you, epidemiology is statistics. And sometimes it's even more complicated than what I'm explaining. And this is the most likely. Most likely, if you get here, just to repeat myself, peak, we got 6, average. The first case, 9, we got 7 as minimum. Last case, 13, we got maximum, 3rd of December. So between 3rd and 7th, this here, the red here, light red, is the most likely period of exposure. Okay, that's just a quick example. We got this example from the CDC. But I put it in the way I think people would understand. Just before talking about investigation of an outbreak, there is one statistic that is very, very important. It's the attack rate. What is attack? Attack. It means, yes, assault sometimes. Assault or attack. We call this, when we are talking about a disease that is coming in large amounts in a small period of time, short period of time, we call it attack. Because large amounts in a short period of time. Attack. We call this attack rate. It's an incidence rate, but very quick and in large numbers. Attack rate in general is number of people at risk in whom a certain illness develops. These are the number of people who showed symptoms because they ate something over the total number of people at risk, which means the total number of people who were in the party or the wedding. We have 100, only 80 got symptoms. 80 over 100. See, sometimes you want to know the attack rate for each food. In the party, we had 10 foods, 12 foods, depending. So you want to calculate the attack rate for each food, which means the number of people who got sick from that food, ice cream, over the total number of who ate that food, not the total people who are at the party. Because some people, they didn't eat ice cream. We call this food-specific attack rate. Okay, based on this, let's have a look. Of course, we have primary case, which is you in the party, and secondary case, which is your sister or your brother or your mother at home. She got the disease from you, which is rare. We talked about this 2 lectures back. Okay, so primary case, which is the one in the party, and secondary case, the one who got the disease from the primary case. Okay, have a look at this. Maybe I have to move this up here. Okay, so if you look here, good. And this, and this, and finally this. Okay, if you look here, you have people who ate something which is they are exposed to, and people who did not eat something or eat food, of course, they are not exposed to it. Exposed, not exposed, which means ate, did not eat. And you have beverage, drinks, and you have egg salad, two foods. We have to calculate attack rates, very important. So those who were sick because they drank beverage, 179 out of the total, or those who drank, 264. So 179 over 264 times 100%, 68. And the same for the egg salad, 78. And the same for the beverage, but those who are not exposed, 44 and 37. See, really something strange. Some people did not eat, but still they are sick. Maybe secondary, who knows? So don't expect that people who eat spoiled food, don't expect that those who eat this 100% will get sick. No. And those who do not eat will not get sick. No. We are talking about relative thing. So this is life. If you look here at the exposed, ate, you will see it's 68 and 78. If you look at the not exposed, did not eat, 44, 37. Which is higher? Exactly, those who ate, who are exposed. But can you tell if beverage or egg salad were the cause? You cannot. We can tell those who were exposed, who drank beverage or ate egg salad. But is it beverage? Is it egg salad? We cannot tell. How do we tell? Well, it's cross-tab. Let's continue, and we'll get back to this table in a minute. Occurrence of disease. You remember, all of you, in the first lecture of this chapter, the definition of epidemiology. One of the FD2, D number one is distribution. And I told you at that time, distribution is governed by a model called PPT, person, place, time. Okay, person, place, time. So the person is us, sex, age. If you look at this curve, this is pertussis, and this is the one, the pinky curve, this one, or the purple curve. It's only those who are less than 1 year old. It means that this disease is mainly in children. And the same thing here, mainly in children. If you look here, this is gonorrhea, sexually transmitted disease. Before 2013 or 2012, mainly, it's more, not mainly, more in females. After 2013, it was vice versa. Males are. So sometimes sex interferes. Still, we are talking about who? Same thing for leishmaniasis in Jericho. This is one of our publications which we did 10 years ago, and we found that it's more in males, 526 compared to 391. Okay, and in the age less than 14 years, it's mainly children. So this is mainly children. Look, as you go down, the number of cases become less. So it's you don't expect this to become zero, no. But if you look at this, most of the cases are 0 to 4, 5 to 6, half of the cases maybe. So this is sex and age in leishmaniasis. This is also time. If you look here, this is aseptic meningitis, which is caused by viral meningitis. If you look here, the peak, it's mid-year, maybe in summer, maybe. And in winter, it's low, the lowest number of cases. Up, down, up, down. So it's a pattern. It's an intermittent pattern, a pattern that is repeating itself over the years. Lowest in winter, highest in summer. Lowest in winter, highest, exactly like the diarrheal diseases in summer and respiratory infections in winter. Okay. And if you go to leishmaniasis again, in Jericho and Palestine, you will see that it's mainly in winter. 91 cases in January and 102 cases in December. It's even giving you a parabolic shape. You know the parabola in mathematics, the parabola? Parabolic shape, with the apex down to summer. So in summer, we don't see cases, or we see cases still, but not like in winter. Okay, so this tells you that time is also very important. Now, place. This is United States of America, And here we are talking about Lyme disease, which is caused by Borrelia, borreliasis, Borrelia recurrentis, Borrelia burgdorferi, and others. You can see that it's only northeast of United States. Minnesota, Wisconsin, Illinois, New York, Pennsylvania, New Jersey, Connecticut, Massachusetts here. You can see also New Hampshire. All of these, this disease is prevalent in these states, but not, let's say, Texas. Texas is desert. California a little bit mainly, and so on. So it's northeast of the United States, Lyme disease. So geographically bound, a geographically bound disease. The same for malaria. See the blue areas here? It's an African disease, 94% of the cases, and 6% all over the world. So malaria is an African disease, okay, according to WHO. So these are the steps of the outbreak investigation. Investigation means you are going to ask questions just like a police, or investigation is like interrogation, you know. So first you have to define the outbreak. What does it mean? You have to define the case. What is a case? It's somebody who shows symptoms, for instance. Let's say diarrhea or vomiting or abdominal unrest and so on. That's definition. Plus you can add tests. These are enteric diseases, enteric bacteria. You can say, and positive, let's say, for any of the enteric bacteria, Escherichia coli, Salmonella, Shigella, Campylobacter, and others. So this is the definition. And you have to define your numerator, those who have the disease, numerator, 1/2. 1 is the numerator, over 2 is the denominator. You have to define your denominator. Those people who were at the party, those people who were in the wedding. So this is so you have to define this, okay? And this will allow you to make your calculations. Attack rate. Attack rate is the main calculation here. Then you examine person, place, time, exactly in the way I showed you. Yes, all the people were in the church, all the people were in the mosque, all the people were in the temple, and so on. Place and time. All the people were, let's say, in the evening in the party. Okay. And then generate hypothesis. How do you generate hypothesis? From two things. You make good literature review of similar cases, because here you know that the causative agent may be stick or Escherichia coli or Salmonella. So you go back and read about Salmonella outbreaks. That's first. And then you have to make a questionnaire, an interview, and sit with each one and ask him or her those list of questions. Okay. And then test your hypothesis. Test your hypothesis. First, you have to use lab tests, very important. And then case controlled study. Maybe you can use these people who attended the party and make another group which did not attend the party and make a similar study and see the difference. This is what we call case control. You have cases and you have controls. People who were in the party and people, maybe you select them, people who are not in the party, another 100 people, and just treat them as the same. There you will find numbers very low. It doesn't mean that you are going to find them zero, no. And here in the party, you will find numbers very high, and then start comparing. Then control. After this investigation, the main thing is to control this outbreak, to stop it, to stop this outbreak, to control it. So you have to control this outbreak which you are investigating, and get an experience to stop similar things that happen in the future. Okay. And then very important to write a report, because if you do this, if you are going to be an investigator, you cannot say, oh guys, I'm going to investigate by myself. No, you will be assigned as an investigator by the Minister of Health, by an authority, any authority in the country. Okay, usually Minister of Health, usually, but any authority. Okay. And then once you write the report, very good is you present, not very good, it's a must. You present or you submit this report to the Minister of Health and the health authorities in the country. You may, let's say, you make a publication and put on the PubMed so that people will know your efforts and how you got about and how you dealt with this outbreak that is caused by Salmonella, so that other people in Venezuela, in Chile, in China, in Russia will make use of your knowledge. Okay, that's very important. Very, very important. So that other people know how you did it. Okay, you were a successful guy or a lady, and the people had to know how you did this so that they can benefit from your experience. Okay, and you can put it even sometimes on social media, Facebook, LinkedIn, this, that. Okay, dissemination, very important. If you write a report and put it in the drawer, it's really detrimental, it's catastrophic. Let people know what you did, even sometimes if you are not 100% successful. Now you remember this table. Now come back to the table. You remember this table? Yes? Good. So you had here ate and drank, eating, exposed, and did not eat, not exposed. As I said earlier, that there is difference between exposure and not exposure. Yes, there is difference. 68, 78, 44, 37. But is it beverage? Is it egg salad? We cannot tell. By the way, this is a okay. By the way, this is a pharyngitis outbreak, inflammation of the pharynx, which is usually caused by Streptococcus pyogenes, gas, group A, Streptococcus gas, and it happened in a jail in Miami, Florida, in the United States, 1974. Yeah, for some 40 years, 50 years ago. Okay, so if you look here from this table, you can see clearly that those who are exposed they are higher. Yes, they have attack rate higher than those who did not eat. But which is which? Is it beverage? Is it egg salad? We have to make a cross tab. 2x2 contingency table. This one here. Tabs, cross tabs. Let's have a look. How do we make them? This is a cross tab. Look at the yellow squares or boxes. So you can see here, drink vertically, drink, not drink, vertically, beverage. And you can see horizontally, egg salad, no egg salad. So you have vertical, you have horizontal. And you can see here, those who drank, 152 got sick. Out of the total who drank 201, so we got an attack rate of 75.6. which is 152 over 201 times 100%, which is 76 almost. And the same for each of them. Easy to calculate, yes? Now look vertically. Turn a blind eye. Close your eyes on the salad. Don't look at the salad. Look at the drink, vertical. Drink, no drink. 75 or 76, 80. Is there a difference? Big difference? No big difference. 26, 25. Big difference? No big difference. So the drinking vertically did not do anything. 76, 80, 26, 25. It's almost the same. Now, go horizontally. Close your eyes on the drink. Don't look at the drink and look at the egg salad horizontally. 76, 26. Is there a difference? There is a significant difference. Look so. 80 and 25. The same thing. There is a big difference and there is significant difference. So it's the salad that made the difference. So is it the beverage or the salad that caused the problem? It's the salad. From the previous table, you cannot tell. You have to make a cross tab, 2x2 contingency table, to be able to find which of the two foods here is responsible for the outbreak. It turned to be here, that is the salad, egg salad. See, this is what I mean here. Egg is the main suspect. Look, I have a video. You can go and have a look at it. Just let me show it very quickly. An example. This is an example in the book, which I made, let's say, in a better way. Let's have a look. Usually there is my voice here, but I'm going to mute it so that I can explain and not have double voice. Okay. So click, and then it goes like this. Move it here. Okay, attack rate, solving a problem, problem one. There are two problems. Attack rate, we talked about this. Illness over people at risk. Food specific rate. Food, those who ate a certain food over the total of those who ate the food. Of course, this specific food, you have to get sick from that for certain food. It's an acute disease. It's like incidence rate, but more acute. Look here. So here we have two tables. This is the total number of people who ate salad, 7,500, and did not eat 100, and those who did not eat egg salad, 250. So 75, 100, 50, and 200. This lower table here, you have the 60, those who ate salad, but they showed symptoms. So you have out of the 75, 60 got disease. Out of the 200, 70 got disease. 100, 75 got disease. 50, 15 got disease. Okay. So question 1, what is the sore throat pharyngitis attack? It's similar to the one we explained before. What is the sore throat attack rate in persons who ate both egg salad and tuna? This egg salad and tuna, this one and this one, because this ate tuna, this ate salad, this ate tuna, this egg salad. So, and the second one, just a moment, the second question is, what is the sore throat attack rate in persons who neither ate egg salad nor tuna? Not tuna, not salad, which is the 15 and the 15. Let's have a look and see. Okay, attack rates first. So what is the attack rate? 60 over 75. And here it's going to be 15 over 50. Good. 60 over 75 times 100% times 100%, 80%. And 15 over 50 times 100% is going to be 35. So we have 80 and 35. See, 15 over 50 times 100%. Okay. Now to see which is which food item is most likely to be infected. Look. So make a cross tab. Tuna versus salad. See, tuna versus salad. Tuna and salad. No tuna, salad. Tuna, no salad. No tuna, no salad. So this is going to be 15 over 50 here. Or let's start 60 over 75. 75 over 100. 70 over 200. 15 over 50. That's the way it's going to show. That's the attack rate. All the time in outbreak, attack rates. Be patient and have a look here. 60 over 75. 75 over 100. 70 over 200. And 15 over 50. This is the attack rate. Times 100, times 100%, times 80, 75, 35, and 30. Now, have a look. Look horizontally, which means tuna. Your eyes are closed from the salad. Close your eyes and open it for the tuna. 80 to 75. Any difference? No. 35 to 30. Any difference? No. Now, open your eyes here and close it here. No significant change. Yes, it's obvious. See, look vertically. Open eyes here, close them here. 80, 35. There is difference. 75, 30. There is difference. Then, so it's salad, not tuna. This is how it's gone. You can have a look at this video. My voice is there. Or you can see it here if you like. Salad is most likely to be infected. Okay. Let's go back to where we were. There's another example. Which is a mass in a church. Few believers, Christian believers, were in a church. After they did the mass, they went to a party and they ate 14 types of food. Yes, 14 types of food. If you look here, sick over total, sick over total, sick over total. Look at the vanilla ice cream. Sick, 43 persons of the total 54, which is 80% attack rate. At the same time, those who did not eat, don't expect it to be zero. Still, some people who did not eat will get problem from that food. Yes, that's life. 3 over 21, 14. So you are talking about 80 compared to 14. Attack rate of 80, attack rate of 14. what do we do now? We calculate what we call in epidemiology relative risk, which is the attack rate of 80 over divided by the attack rate of the who did not eat. Attack rate of eaters, which is 80, over divided by attack rate of non-eaters, which is 14, which is going to give us a number. See, sick, not sick, vanilla, not vanilla, eating, not eating. We took this from the table above or previously. And 80 and 14. Look, this is the attack rate. 80 over 14, 5.6, which means that those who ate vanilla ice cream, 5.6, the probability is 5.6 times more than those who did not eat. Does this mean those who do not eat will never be sick? No, still they will see. Still you will see people who are sick and did not eat from the food that is suspected. That's life. You can never judge. Okay, so this is another way of calculation. And I think this is it for today, guys, ladies and gentlemen. Any question before we go? Remember, Wednesday, we have the quiz. What time? 13. Yes, 13 hours Jerusalem time. Okay, for how long? 40 minutes. How many questions? 20 questions. 5 questions are nasty questions. Okay, thank you very much and have a nice time. Goodness.
The incubation period is characteristic.
Yes, each disease has
appear normal. Here, he is not communicable. He does not transmit it to
in the look, he appears normal. In the incubation period, by the way, person appears normal. But at the end of the incubation period, he's still normal but infectious. Normal plus infectious.
Okay, what do you mean by contagious in the third?
Contagious infectious. At the end, incubation period is this 2 to 20 to 10. And maybe at 7, 8, 9, 10, he's normal plus he's infectious. Yes, yes. Yes, ladies, gentlemen.